Hey everyone, today we are going to learn about the union find data structure with union by rank optimization. This is a powerful tool used in various algorithms, especially when dealing with connected components or finding cycles in a graph. So let's dive in. So union find is also known as disjoint set union, right? Helps us manage a collection of disjoint sets. So these are all disjoint sets, right, represented in the form of graphs. Think of it like managing different groups where each element belongs to exactly one group. We have two main operations. So here this 1 and 2 belong to one group, 3, 4, 5 belong to one group, 7, 6 belongs to one group, and 8 singularly belongs to one group. Now there are two main operations. There are two main operations in union find, right? One is find itself, okay, but I like to call it find parent, and another is the union, where I like to call it union set, right. What does each of this do? The find parent determines which set an element belongs to. So which set an element belongs to. So for example 1, 2, they belong to set 1, but in this algorithm we represent it as a parent. So 1 can be considered a parent for this particular set, and therefore 2 belongs to this parent, and 1 also belongs to the parent itself, which is 1. We will have a better understanding of this as we move forward with our tutorial. And then we have the union. This combines two sets into one, right? The operation where say this set and this set we have, so we have to combine these sets, right? Once we combine this set, this becomes a singular set. Okay. Now let's have a brief introduction of the algorithm. A brief introduction of the algorithm would mean that say we have two nodes, 1 and 2. Now each node belongs to a separate set, that is set 1 and set 2, right. These are separate nodes. Accordingly, we can say that 1 belongs to set 1, so its parent is itself, and 2 belongs to set 2, so its parent is itself, right. Now we can represent this using an array. We call it the parent array, right. So where we have 1 and we have 2. Okay. In the beginning, before using the algorithm, we set that this one node will have a parent of 1, as it is evident here, and 2 node will have a parent of 2, right. Since we are going to learn union by rank today, we are also going to maintain another array, which is the rank array, and initially the rank is 0 for both 1 and 2, right. Now for the first algorithmic operation, which is find, right, or find parent, when we say find of 1, what do we get? We get whatever is inside the parent array. So in here the answer would be 1, and similarly if we say find 2, what do we get? We get 2, right. because that is what is inside this array as well. So, union would mean that we would union these two separate sets, and the function would look like union 1 comma 2. So, here what can we do? In order to do a union, we can say that we can connect 1 to 2. Okay. Now, the algorithm we will come later, but here just consider, if you look at the ranks, these two are the same, right. Therefore, we can say that since union of 1 and 2, we can say either of them can be connected, as it is evident here can be connected to, and we can consider 1 to be the parent also, and we can consider 2 to be the parent also. Here we will consider 1 as parent. Therefore, when rank of find of 1 is equal to rank of find of 2, we will say that parent of 2 would be 1. Okay. So, what do? We will update this, right. We will set it as 1. Also, we will say that we will increase the rank. So, rank of 1 would increase by 1, that is rank 1 plus 1, right. So, now the graph or the set would look like this. There are two things that you have to keep in mind when you are doing this algorithm is the parent we have to update, and also the rank we have to update, right. And this happens when the ranks of two sets, or then the ranks of the canonical node, which is the parent node. The canonical node or the parent node of two sets are the same. That when I say find 1 and find 2, we mean to say we need the parent of find and we need the parent of 2, and that is how the algorithm is structured. Now, let us start with these elements 1, 2, 3, 4, 5, 6, 7, 8. You have 8 elements. Okay. We will represent each set as a tree, where the root of the tree is the representative of that set, which means that this is a tree and the root of the tree is itself, right, which is also represented by the parent array here, that is parent of 1 initially is initially, right. Okay. Here where it gets interesting. Union by rank is an optimization technique that helps keep our trees balanced, and here how it works. Each node starts with rank 0, as you can see, each node starts with rank 0. Okay. When we union two trees, as we have seen earlier, if the ranks are different, the smaller rank tree goes under the larger rank tree. Keep this in mind, that the smaller rank tree goes under the larger rank tree, right. And also, as we have seen earlier, if the now if the ranks are equal, we can choose either as root, but we increase the rank by 1, which we have seen earlier. This simple rule helps us prevent our trees from becoming too tall or inefficient. Now, let us walk through an example step by step. Initial state, all elements start as separate sets. seen here, they are separate sets, right, and they have 0 as their rank initially. These are all initial values. What do we do first? We have to union two elements. So, what do we union? We will do a union of 1 comma 2. Right. When we do a union of 1 comma 2, as we have seen earlier, what do we check first? We will check the parent of 1, which is 1, and the parent of 2, which is 2. Now, what do we say? We see that rank of say P1 is equal to rank of P2, right. Therefore, we can say that 1 can now become the parent, right, of 2. So, what do? We update the parent of 2 to 1, and this is very important, we have to keep this in mind, increment the rank of 1, right. 1 is increased to 1. Now, what do? We will connect 1 and 2, but we shall do it in a different way. We will do it like this. We have 1 and we have 2, right. Let us represent this connection. Let us represent this connection as this, and this indicates that 1 is also its parent and also 1 is a parent of 2, right. Next, what we will do? We will do a union of 3 and 4. Now, similar process, parent of 3 is 3 itself and parent of 4 is 4 itself, right. Now, the rank of P3 is equal to rank of P4, okay. Thus, we can make either the parent of either, right. Here we choose to make 3 the parent of 4. 3 is now parent of 4, right. What does that mean? We have to make 3 the parent of 4. So, 4's parent will become 3, and we have to increment rank of 3, right. So, what that means is we have to increment the rank of 3 here, it will be incremented to 1, right. Now, we have to draw 3, and now this becomes 4. This becomes 4, right, and this indicates that 3 is a parent of itself, also 3 is a parent of 4, and which is also evident from this array, the parent array and the rank array, right. Now, what do? This is very important. This is a case that we have not seen earlier. We do a union of 1 comma 3, right. So, when we do a union of 1 comma 3, what do? We figure out the parent of 1, which is equal to 1, and we do a parent of 3, which is again equal to 3, right. Therefore, rank of parent of 1 is equal to 1 and rank of parent of 3 is also equal to 1, thus they are equal. Thus anyone can be set out of this, anyone can be set as the parent of either. Okay. So what do we choose to do? We will choose to set 1 as the rank of as the parent of 3. What do? We will choose to set 1 as the parent of 3. Now once we do that, how do you think the array would look like? 3 would have an updated as one parent, and also since there is equality here, there will be an increment in the rank value also. Therefore the rank of 1 will become 2. Okay. Now let us draw the graph again. So we have 1 as the parent, we have 2, we have 3 and we have 4, right. 1 is here, 1 is a parent of 3 as evident here, and 4 here, and 1 is a parent of itself. Okay. Now what do? We will do a union. Now let us take another example, a union of 5 and 6, right. So if we do a union of 5 and 6, what do you think will happen? Similarly, we would have, say, parent of 5, which is 5, parent of 6 is equal to 6, right. Now rank of P5 is obviously 0 and rank of P6 is also equal to 0. They are equal, again equal cases. So what would happen? I will set 5 as the parent of 6 here. Okay. So in this case what would happen? I would go and write 6 whose parent would become 5, and I would increment the rank of 5 to 1, right, and 5 here would become 6. with itself as the parent of itself, right. We will do a union of 1 comma 5, right. Now same algorithm, parent of 1 which is P1 is 1, parent of 5 which is P5 is equal to 5, right. So rank of P1 is 2 as we can see here, and rank of P5 is equal to 1. Okay. Now the case is, see, I say this is R1 and R5. What do we see here? We see that R1 is greater than R5. So when R1 is greater than R5, the algorithm instructs us that we need to connect the smaller set to the larger set. Okay. We need to connect the smaller set to the larger set. So what does that mean? It means that parent of 5 would become 1. Therefore, parent of 5 would now become 1, but there will not be any increment in the rank. So now no increment in the rank, right. Now the final graph that we would see how this would look like, and I think you guys have guessed it right. We have 1 as the top, we have 2 here, we have 3 here, and we have 4 here, right. And now we have 5 here, okay, and now we have 6 here. the connections would look like this, 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 this and this and this. This is the final graph till the point we have processed it. Obviously, we have 7 and 8 left, but that can also be accommodated here according to the unions that we do. But this is the basic algorithm that we are seeing. See, we have merged it on the basis of the rank, okay? On the rank we have merged it. So, what did we come across? If rank R1 is equal to R2, here R1 and R2 can be rank of the two nodes that we are doing union with, that is the parent of these nodes, not the nodes itself, not 1 and 5, but the parent of 1 and the parent of 5, we are seeing the rank of them. If R1 and R2 is equal to, okay, what we do is that we can choose either R1 or we can choose either the node of R1 or the node of R2 to be the parent, okay. And if R1 is greater than R2, what do we do? So, the node of R1, say N1, this becomes the parent now, okay. This becomes the parent of the set to which this node, this parent of that is the node to which R2 is, there we have supplied a node that. So, node 2, this set becomes it. Now, the time complexity in the union find data structure, there are two operations, which is the find and which is the union, and the find has a time complexity of big O of log n, and the union has a time complexity also of big O of log n, because the trees are getting balanced when we are doing the union operation. So, these are much better than the worst case scenario of big O of n, where we would get this without the optimization, okay. Big O of n we would have got had we not optimized it. This optimization is crucial in algorithms like Kruskal's minimal spanning tree. In our next video, we will look at path compression, another optimization that makes this data structure, that is the union find data structure, even more efficient. Don't forget to like, subscribe for more algorithm tutorials.